Hi, I'm Mark Barsamian with the Math Department at Ohio University in Athens, Ohio. This is the first in a collection of videos for a one-semester course in calculus. Here at Ohio University, our one-semester course is Math 1350, Survey of Calculus. But this collection of videos is fairly generic and could be used for a calculus course at another college or even at a high school. And in fact, they could be used for self-study at home. Now, in our course at Ohio University, we do use a commercially available textbook, but the videos don't in any way depend on an accompanying textbook. You'll see that the videos are centered on a collection of written notes. During the course of the video, I write on the notes. The notes look like this. There are graphs, there's printed words, there are mathematical equations. I write on these with a pen in the course of the video. Well, you can go online and view or download a PDF file of those notes that were produced in the video. And then you can read the PDF file and study that. Now, to find that PDF file, you'll go to the YouTube page for this video, and in the details about the video, you'll see a link where you can view or download that PDF file. In this first video, I'll be introducing what are called limits. We'll be taking what I would call a graphical approach to limits. That is, the functions that are involved are described by graphs, not by formulas. Okay, here we go. Limits Video A, a graphical approach. Our topics in this video will be the terminology and notation of functions, the definition of limit, and then various examples involving limits for a function given by a graph. And as I said at the start of the video, to view or download this PDF file, you can follow the link that is provided in the description portion of the web page for the YouTube video. You may need to click Show More to reveal the link. The terminology and notation of functions that we'll use is fairly basic. Remember that a function, f, can be thought of as a machine that takes input that's a number from a set of real numbers called the domain, and produces as output a number that's in a set of real numbers called the range. We can visualize this situation with what I would call a machine diagram. In this diagram, you can see this letter x, that's a symbol denoting the input, being fed into this machine that has the symbol f, that's the name of the function, and then coming out of this machine, this symbol f parentheses x, now that's spoken f of x, that denotes the resulting output. That's a number in the range set. It will be very important in our calculus course to be comfortable with the idea of displaying numerical functions on graphs. To do that, you make a set of axes, and the horizontal axis is used for the input numbers. Now, often the input variable is called x, and so we'll often refer to the horizontal axis as the x-axis. But x won't always be the variable. In some examples, the variable might be, for instance, t for time. So then the horizontal axis would be the t-axis. So again, the name can vary, but it is the input axis. Now, the vertical axis is used for the output numbers. Often those are called y, so we often refer to the vertical axis as the y-axis. But again, that won't always be the case. There are examples where the vertical axis could be maybe capital C for concentration of some chemical, or it could be N for number of something sold. So the vertical axis may have different names, but the key thing is that it's always used for the output numbers. Now, how do we actually display the function on the graph? Well, the key thing is this. If an input number x equals a causes an output number of b, that's denoted by f parentheses a, or f of a, so we'd say f of a equals b, or the resulting output is b. If you have that situation, then the point with xy coordinates a comma b is on the graph, and vice versa. So in this picture, we can see the number x equals a was used as input, and the resulting output was the number b, that's denoted by the symbol f of a equals b. And we see that there's this point with xy coordinates a comma b, that's a point on the graph. So for instance, this symbol, spoken f of 2 equals 7, would tell us for the function called f, an input that's the number x equals 2 would cause an output that's the number y equals 7. And that symbol would also tell us that the point with coordinates 2, 7 is on the graph of the function. Now we're ready to discuss limits. We'll start with the definition. First of all, the symbol for limits. The symbol consists of the three letters LIM, that's an abbreviation for the word limit. Below that is this symbol, x arrow c. Next to that is the symbol f of x. Next to that is the symbol equals L. This symbol is spoken in the following way. The limit as x approaches c of f of x is L. So those four components that I talked about, the LIM, the x arrow c, the f of x, and the L, they all show up in the way that you speak the symbol. Now there's a less abbreviated symbol that's not really used, but I like to introduce it because it is maybe clearer. It's this symbol, f of x arrow L as x arrow c. This is spoken f of x approaches L as x approaches c. Now before I tell you what this symbol means, I need to tell you what the various parts are that make up the symbol. That is, this x, this c, this f of x, and this L. That's what I refer to as the usage of the symbol. When you want to write a symbol like this, what are the parts that you have to have available in order to build that symbol? Well, in that symbol, the letter x is a variable, f is a function, so we see then that this symbol, f of x, would be the resulting y value. The letter c denotes a real number, and the letter L denotes a real number. So that's what I would call the usage. When you want to build that symbol, what parts do you need to have? Finally, the meaning of the symbol. What this symbol means is the following. As x gets closer and closer to c, but not equal to c, the value of f of x gets closer and closer to L, and may actually equal L. So notice that this symbol is an abbreviation for these spoken words, and that is actually an abbreviation for this longer spoken sentence. So the definition of limit is that written sentence. Notice that sentence does not have the word limit in it. This is just a sentence of prose and some letters, and it's abbreviated using this sentence involving limit, and that's abbreviated using this symbol involving LIM. So the key thing is to remember that the concept of limit is an abbreviation for this kind of behavior. Another thing that I will add to this definition of limit is what I would call graphical significance. That is, what will this mean in terms of the graph of a function? We'll come back to this later after a couple of examples. In this video, we'll explore limits using a graphical approach. That is, the function f is given by a graph, not by a formula. Let's go on. We'll start by considering examples of the following kind. Given a graph of a function, our job will be to give a description of limit behavior of that function. Our first example will be an extended example involving limits for a function given by a graph. It's this function given by this graph. Our job will be to fill out this entire table. Notice this table has a bunch of rows. Each row has a particular x value. We'll start by filling out this row of the table, the row that has x equals 1. So we're going to start with the row for x equals 1, and our job then is to fill in this row of the table. Now we will concentrate on these two cells because those are cells that we know about. These two cells we don't really know about yet. We'll discuss those later in the video. To fill in this cell, we realize that we need to find a y value. This symbol, f of 1, stands for the y value when x is 1. Well, so we need to go up to the graph and find the grid line for x equals 1. That's that grid line. So observe that the graph has no y value at x equals 1. There is no point on the graph at x equals 1. This open circle is there to tell us that there's kind of a surprise in the graph, that is the place where you might expect the graph to be, the graph is not there. So there is no point on the graph at that location. Well, since the graph has no y value at x equals 1, we have to conclude that f of 1 does not exist. That is, the y value does not exist. That means that in the cell of the table for the y value, we write the following. We write DNE for does not exist. Now what about this cell of the table? We have to find what goes here. Now remember what this symbol means. This symbol is the limit symbol. Let's go back up and look at the definition. There's the symbol, and what it means is this. As x gets closer and closer to c, but not equal to c, so that's denoted by that part of the symbol, the values of f of x get closer and closer to L, and may actually equal L. So there we see the f of x. Now notice that in our table, we're missing this. So our job in the table is going to be to figure out what number L would go there. So our job, again, is to figure out what will go in this spot on the table. Well, to figure that out, we need to investigate what happens on our graph when x gets closer and closer to 1, but not equal to 1. Let's draw some lines on this graph to figure that out. Here I've zoomed in on the graph in the vicinity of x equals 1. Let's choose an x value that's close to 1, but not equal to 1. So for instance, there, that blue x value. Let's figure out what the y value is for that x value. The y value comes out up here, close to the number 3. But we're supposed to investigate what happens as x gets closer and closer to 1. So let's choose an x value that's even closer to 1. For instance, that purple x value. We see that when we use that purple x value as input, the resulting output, the y value, is even closer to 3. Now, we need to consider all x values getting closer and closer to x equals 1. So we should also go on the other side of x equals 1 and try out an x value that's larger than 1. Maybe that green x value. Let's see what y value it causes. Well, its y value comes out up there, close to 3. Let's choose an x value that's to the right of 1, but even closer to 1. Like maybe that red x value. So observe that when x values get closer and closer to 1, but not equal to 1, the y values get closer and closer to 3. Now it's key to remember that when x actually equals 1, we don't get a y value. So in words, here are observations about what happens when x gets closer and closer to 1, but not equal to 1. When x gets closer and closer to 1, but not equal to 1, the y values get closer and closer to 3. Well, realize that this sentence is abbreviated by the following limit symbol. So this symbol, spoken the limit as x approaches 1 of f of x is 3, is an abbreviation for this word description of the graph behavior. Now, in this kind of situation where the graph has kind of an exceptional point, that is a place where we'd expect there to be a point on the graph, but in fact there is not one there, we could refer to that as a hole in the graph. So we would say that the graph has a hole at the location x, y equals 1, 3. So notice that I am careful to say hole at the location x, y equals 1, 3. I don't use the word point. I don't say that there's a hole at the point 1, 3, because I don't want to be unclear. There is no point there. That's the reason we're emphasizing this. There's a hole at that location. So we have filled out the two cells of the table that I said we would fill out. We'll come back later and address those two cells. Let's go on. All right, now we're going to do the row of the table for x equals 4. As with the previous page when we were discussing the row for x equals 1, we will focus our attention on just these two cells of the table. We won't worry about these two. So as we did in the previous page, we'll start by filling in this cell. That is, we need to find the y value when x equals 4. So we start by finding the grid line where x is 4. That's here, and we look for a point on the graph that has x-coordinate 4. Well, we see that that's this point here. There's a point on the graph at the location xy equals 4, 2. So that tells us that the y-coordinate is 2. F of 4 equals 2. So what I need to put in this cell of the table is equals 2. Now let's turn our attention to this cell of the table. We need to find out what goes here, the value of the limit. So this limit is about observing what happens when x gets closer and closer to 4 but not equal to 4, noticing what happens with the y values. So we need to zoom in on the graph in the vicinity of x equals 4 and study what happens with the y values. So as we did in the previous page, we'll choose an x value close to 4 but not equal to 4. How about that blue one? We find the corresponding y value that results. The y value comes out over there, close to the number 1. Let's choose an x value that's even closer to 4 but not equal to 4. Maybe this purple one. Let's find the output that results from that. We see that the y value comes out even closer to 1. Now, as we did on the previous page, let's choose x values that are greater than 4. For instance, that green x value is close to 4, but a little bit greater than 4. Let's see what its y value is. We see that its y value comes out close to 1. So let's choose another x value that's even closer to 4, but on the right side of 4, like maybe that red one. We see that it produces a y value that's even closer to 1. So our observation is that when x gets closer and closer to 4, but not equal to 4, the y values get closer and closer to 1. And again, note that it's key to have the qualifier that x is close to 4, but not equal to 4. We already know what happens when x actually equals 4. We get a y value of 2. So our description of what's happening when x is close to 4, but not equal to 4 is this sentence. When x gets closer and closer to 4, but not equal to 4, the y values get closer and closer to 1. Well, remember that that whole sentence can be abbreviated in symbols using the notation for the limit. This 4 goes there in the symbol, and this 1 goes here. So we see that this symbol, spoken, the limit as x approaches 4 of f of x equals 1, is the abbreviation for that prose sentence. Again, notice that there is no point on the graph at that location. That's kind of a surprise, so we call that a hole. We say there's a hole in the graph at 4, 1. So in terms of the symbols, we see that this point with x-coordinate 4 and y-coordinate 2 is reflected in this symbol. There's the x value and there's the y value for that point. And we see that this behavior is reflected in this symbol. This number here is the x-coordinate, and this number here is the y-coordinate of this location that the graph appears to be heading for. So notice that I don't say that it's the point that the graph is heading for, it's the location that the graph is heading for. So we've filled in the 2 cells that I said we would fill in. Again, we're not going to fill in these cells right now. Let's go on. Now I want to go back and add a line to the definition of limit. Earlier I said that we would come back later and fill in the graphical significance. Let's go back up and look at the 2 examples that we've done so far. Notice in this row of the table, when x is 1, we had the limit as x approaches 1 of f of x equals 3, and the behavior of the graph could be described in the following way. Notice that as x gets closer and closer to 1 but not equal to 1, the graph seems to be heading for this location. So that really is what's embodied in that limit symbol, in the idea of limit. The limit encapsulates the trend of the location that the graph seems to be heading for. And in the next example, the row of the table where x equals 4, notice that when x is getting closer and closer to 4 but not equal to 4, the graph appears to be heading for this location. And so again, the limit encapsulates that idea of that trend. Where does the graph appear to be heading? So that is what I'm going to put in this definition of limit here by graphical significance. That is, this symbol, spoken, the limit as x approaches c of f of x is L, has this significance in terms of the graph. The graph appears to be heading for the location xy equals CL. So whatever the letter C is that appears in the limit symbol there, and whatever the letter L is that appears in the limit symbol there, those are the x and y coordinates of the location that the graph appears to be heading for. Notice that I keep saying location, I don't say point, because when you finally get to that location, there may or may not be a point there. Doesn't matter. The limit is about the trend in the y values. This symbol is about the trend. So that's a key difference from the symbol f parentheses c. This symbol denotes the y value right at the x value, x equals c. Let's go on. Now let's do the row of the table for x equals -1. That is this row of the table. We'll focus on these two cells. So to find the y value, we need to first locate the grid line where x equals -1 and then find where that grid line touches a point. Here's the grid line for x equals -1. And we see that on that grid line, there is this point at the location -1, 1. So that tells us that f of -1, that is the y coordinate, is the number 1. So we put a number 1 in this cell. So there's our point on the graph at the location xy equals -1, 1. Now let's figure out what goes in the cell there. We need to find the value of the limit. That means we need to consider x values close to -1 but not equal to -1 and see what's happening with the resulting y values. Well, for that we'll zoom in and we'll choose x values close to -1 but not equal to -1. For instance, this blue one. That's close to -1 but not equal to -1. We see what y value results from that x value. We see that the y value comes out here, close to the number 1. Let's choose an x value even closer to -1, for instance, this purple one, and see what y value results from that. We see that the y value comes out even closer to 1. So it seems like the y values are getting closer to 1. But wait a minute, we need to consider x values on both sides of -1. Let's look at an x value over here on the right side of -1, for instance, this green one. Let's see what y value results from that. We have to go all the way up to there and over. We see that that y value comes out close to the number 2. And let's choose another x value even closer to -1, but again on the right side of -1. For instance, maybe that red one. Let's see what y value results from that. We see that the y value comes out even closer to 2. All right, so our observation has to be this. When x gets closer and closer to -1, but not equal to -1, there is no single y value that all the y values are getting closer and closer to. Or we could say this, as x gets closer and closer to -1, there is no single xy location that the graph is heading towards. Well, since there is no single y value, there's no single xy location, that means that there is no number that we could put there that would work. Because remember that the number that's supposed to go here is the y value of the location, the single location that the graph is heading towards. Since there is not a single location, there's no number that would work here. So what do? Well, we have to do the following. We write the letters DNE, which stands for it does not exist. That is, the limit as x approaches -1 of f of x does not exist. There is no y value that would work in this spot. So we say that the limit does not exist. There is no single xy location that the graph is heading towards. Now, for this row of the table, we're actually not going to ignore these two cells of the table. We're going to turn our attention to that now. So as we just observed, the limit does not exist because there's no single xy location that the graph is heading towards. But there are some obvious trends in the graph. One trend is this. On the left side of x equals -1, the graph appears to be heading for the location -1, 1. Let's go up and look at that. On the left side of -1, the graph is heading here. The graph is heading for the location -1, 1. On the other hand, on the right side of x equals -1, the graph is heading for a different location. The graph is heading for this location that has x, y coordinates -1, 2. So we have this trend. On the left side, the graph appears to be heading for this location, and this trend on the right side of x equals -1, the graph appears to be heading for this location. Well, so those are trends, and remember that limits are about trends in graphs. So it would be nice to have some terminology and notation for these trends. Well, that's the idea of what are called one-sided limits. The definitions follow on the next page. The definition of limit from the left, first the symbol. The symbol looks very much like the regular limit symbol. There's just an additional feature. There's a superscript minus sign on that letter C. So this symbol is spoken, the limit as x approaches C from the left of f of x is L. So this superscript minus sign shows up in the way you speak it by just there being this extra phrase in the spoken version. What does that symbol mean? Well, it means the following. As x gets closer and closer to C, but less than C, the value of f of x gets closer and closer to L. So again, that minus sign shows up in the meaning with this extra phrase, but less than C. What's the graphical significance? Well, the graphical significance is the following. The graph of f appears to be heading for this location, C, L, from the left. So we see that this limit symbol for a limit from the left has this letter C and this letter L that show up as the x and y coordinates of a location that the graph is heading towards. The only change now is that we have this additional qualifier, the minus sign, the superscript minus sign, which indicates that the graph is heading for that location from the left. So you still pick out the C and the L from that symbol to build the xy coordinates for a location, but then you have the additional information that the graph is heading for that location from the left. There is an entirely analogous definition for the limit from the right. That's denoted by this symbol, which looks like the regular limit symbol with this extra feature, a superscript plus sign above that C. This symbol is spoken, the limit as x approaches C from the right of f of x is L. And what it means is, as x gets closer and closer to C, but greater than C, the value of f gets closer and closer to L and may actually equal L. And the graphical significance is that the graph appears to be heading for the location C, L from the right. So again, in interpreting this symbol, you still notice the C and the L and recognize that those are the xy coordinates of a location that the graph is heading towards, but with the additional qualifier that the graph is heading for that location from the right. So with that additional terminology of limits from the left and right, we can fill in these two rows of the table. Let's put our trends on this graph. So the graph is heading for the location -1, 1 from the left, so that -1 shows up in that part of the symbol, and that 1, that y coordinate of the location that the graph is heading towards, shows up here. The limit from the left is 1. This cell, remember, corresponds to the trend as x is closer and closer to 1 from the right. Let's indicate that on the graph. The graph is heading for that location. That number -1 shows up in the limit symbol there. That number 2, the y coordinate of the location that the graph is heading for, shows up here. So we say that the limit from the right is 2. Let's go on. Now that we have the terminology of one-sided limits, we can recast the definition of limit as a sort of three-part test involving one-sided limits. So here's the definition of limit rewritten. The same symbol, spoken the same way, means this. The function passes this three-part test. The first test is the limit from the left exists. That is, this symbol exists. The second test is the limit from the right exists. Now here I have a typo. This should say right. And the third test is that the values of the limits from the left and right match with the common value of L. That is, the limit from the left is L, and the limit from the right is also L. So that's the definition of limit, recast as a three-part test. So realize that anytime this symbol is true, then we know the following. This is true, and this is true. Let's go on. Well, now we can go back and fill in the empty cells in the table in the rows where x equals 1 and x equals 4. Remember that when we filled in those rows before, we filled in these cells, but we did not fill in these cells. We'll now realize that we can fill those cells in. In the first case, in this row, we know that limit exists, so that must mean that the left and right limits both exist, and they also have that same value. So we can put equals 3 in these two cells. And earlier we found that the limit as x approaches 4 of f of x is 1. Well, that must mean that the left and right limits both exist, and they are also 1. Let's go on. Now we'll do a new row of the table, the row of the table for x equals minus 3. This row, let's fill in all the cells. Well, we need to find the y value when x is minus 3, so we identify the grid line where x is minus 3. That's this grid line. And we see that there's a point on the graph at the location negative 3, 3. So that tells us that the y value when x is minus 3 is the y value of 3. So we put a 3 in that cell. Now what about these cells? Well, let's consider the trend as x gets closer and closer to 3 but less than 3. Where's the graph heading for? Well, let's zoom in. We see that to the left of x equals minus 3, the graph is heading here for that location, negative 3, 3. On the right side of x equals negative 3, the graph is heading for the same location. So from the left and from the right, the graph is heading for this location, negative 3, 3. Well, remember how we abbreviate that. That x-coordinate of minus 3, that the x-coordinate of the location that the graph is heading for, shows up in the limit symbol there. That y-coordinate of the location that the graph is heading for shows up here. So we write the following. The limit from the left is 3. And similarly, the limit from the right is also 3, because the graph is heading for that same location from the right. Now, since those two one-sided limits match, we say that the limit, the regular limit, exists, and its value is that common value. The limit as x approaches negative 3 of f of x is 3. All right, we've finished that row of the table. Let's go on. Let's do the row for x equals 6. I'm going to do this a little bit quicker. We first identify the grid line where x equals 6. And we notice that along that grid line there is no point. There's no point on the graph with x equals 6. So the y value does not exist. Now let's consider the limit from the left. Let's observe the trend in the graph as x gets closer and closer to 6 from the left. We see that as x approaches 6 from the left, the graph is heading for this location. The xy coordinates of that location are 6 and 0. So we put those xy coordinates of that location in this limit symbol. The x coordinate goes there, the y coordinate goes there. We say that the limit is 0. So there are the x and y coordinates of that location that the graph is heading for from the left. To fill in this cell, we zoom in on the graph and observe the trend as x gets closer and closer to 6 from the right. Okay, we notice that the graph is heading for the location 6, 2, so we use those numbers, 6 and 2, to build this limit expression. The limit as x approaches 6 from the right, there's that number 6, is 2. There is the x and the y coordinate of that location that the graph is heading for. Notice again, I was careful to not say the point that the graph is heading for. There is no point at that location. Now our last job on this page is to fill in that cell. Notice that these two limits both exist, but they don't match. So we say that the limit does not exist. And that concludes the row where x equals 6. Let's go on. We can gather up all of our results in one table. Here it is. Notice again the distinction between the y value and the limit. The y value, remember, refers to the behavior of the graph at a particular x value, whereas the limit refers to a trend in the graph as x gets closer and closer to some x value, but not equal to that x value. So we've seen examples where the limit does not exist, but the y value does exist. We've seen examples where the limit does exist, but the y value does not exist. We've seen examples where the limit and the y value both exist, but they have different values. And we've seen an example where the limit exists and the y value exists and they have the same value. In our most recent row of the table, we saw an example where the limit does not exist and the y value also does not exist. So they're independent of one another, the existence of the limit and the existence of a y value. All right, that's the end of that extended example. We'll wrap this video up with one more example of a different type. That is, given a description of the limit behavior of f, sketch a possible graph of the function f. So here's the example. Sketch a graph that satisfies all of these conditions. F of 1 equals 3. The limit as x approaches 1 from the left of f of x is 2. And the limit as x approaches 1 from the right of f of x is negative 1. We start by noting that in the given information, 3 xy locations are implicated. What do I mean by that? Well, this symbol, f of 1 equals 3, is about this location, xy equals 1, 3. This symbol, the limit as x approaches 1 from the left, is 2. That's about this location. That's an x-coordinate and a y-coordinate of a location on the graph. This symbol, the limit as x approaches 1 from the right of f of x is negative 1. Well, that's about this location. We have an x-coordinate and a y-coordinate of this location on the graph. Well, I start a solution of this kind of problem by plotting these 3 locations with open circles. So there's that first location, there's the second location, and there's the third location, plotted with just open circles, and I label them with their xy coordinates. And then we add features that convey what the given information tells us about these locations. So for instance, this symbol tells us that there's a point in the graph at the location 1, 3. That means we're going to fill in the open circle at that location. So there, we've filled in that circle. This symbol tells us that the graph is heading for this location from the left. So we draw some sort of smooth curve that's heading for that location from the left. So here I've done this. Now notice that I've drawn an arrowhead indicating that that graph continues to the left there. But this symbol is about the behavior as the graph is heading for x equals -1. So that's really about this. So you see that this little tail that I've added that has an arrowhead on it pointing off that direction, we really think about that this way. When we're heading towards x equals -1 from the left, we're heading for this location. Finally, this symbol tells us the graph is heading for this location from the right. So we draw a smooth curve that's heading for that location from the right. So that's this curve. Notice that we should think of this as heading for this location. So this arrowhead indicates that that curve continues on over here. But we are thinking about this symbol in terms of this behavior, that the graph is heading for this location from the right. So there we go. There's our finished graph. Notice again, I didn't write this, but I labeled the x-coordinates of those locations. Maybe I should go back up and add that in my description. So you want to label the locations with their xy coordinates. And there's our finished graph. One last question. Can we fill in all the open circles? For instance, can we fill this circle and this circle? Well, the answer is no. If we filled in more than one circle, that would mean that for x equals 1, there's more than one y value. A y value of 3, y value of 2, and a y value of -1. What's wrong with that? Well, that would violate the definition of function that says for a particular input, there's exactly one output. Put another way, this would violate the vertical line test. The vertical line x equals 1 would intersect the graph more than once. So we're not allowed to put those blue dots in those two locations. Now there's another thing that we should think about, that is, this graph looks very simple, but you might think about, could you have drawn this graph some other way? Well, yeah, I mean, you could have maybe, instead of having this line here, could have maybe made it go up like that. Or maybe instead of this one, we could have the graph doing this. There's lots of different ways that those little tails can look. But there are some things that you have to be careful to not do. So for instance, you might think it would be simpler to just have these tails continue on past the point. For instance, this top one maybe do this, and this bottom one maybe do this. Well, that looks nice, but realize that that violates the vertical line test. This vertical line touches the graph more than once, and this vertical line touches the graph more than once. So those blue extensions, although they look perfectly reasonable, they are not valid as part of the graph of a function. Remember that our graph was supposed to be the graph of a function, f of x. So the finished product needs to be a drawing that qualifies as the graph of a function. Well, that's the end of that example. Well, that concludes this first video about limits. In the collection of videos, this will be titled Limits Video A. The next video in the collection will be Limits Video B, and in that video we'll discuss limits from what I would call an analytic standpoint. That is, the functions involved are described by formulas, not by graphs. Thank you.